Motivation and challenges of identifying fault sections in distribution networks with wind generation. The identification and location of the fault section in either the main feeder or a branch is a problem that has not been effectively solved to date, especially when measurements are made only in the distribution substation. The challenges increase due to uncertainties in input data, such as conductor impedances and the loading of each branch. Additionally, inherent errors arise from the fault impedance and the system load level at the time the fault occurs, which further complicate the fault detection process. As shown here, there are no smart meters installed in the system to help with data acquisition, meaning that measurement is only possible at the substation. Contributions. This paper presents a methodology for fault section identification in distribution networks with wind generation, taking into account inverter-based interfaces such as double-fed induction generation and permanent magnet synchronous generator machines. The methodology uses instantaneous phase current measurements, which are only monitored at the distribution substation. To extract features, we use the discrete wavelet transform over 2 cycles of 60 Hz with 256 samples, 1 cycle before and 1 cycle after the fault detection. The entire spectrum of wavelet coefficients is used to calculate the energy in per unit and the relative energy entropy in per unit, which serve as inputs for training and validating the artificial neural networks to identify the faulted section. We also introduce proposed regularization indexes, such as the routing index for energy in per unit and the potentiation index for the relative energy entropy in per unit, which help highlight the differences between the phases involved in the fault and those not involved. Results and conclusions. The results demonstrate that the artificial neural networks architectures achieved an acceptable performance with an accuracy of 94.8% for fault identification and a maximum error of 5.2% for fault location. These results were obtained using 128 samples per cycle for both training and validation, with 1 cycle before and 1 cycle after fault detection. The robustness of the proposed methodology is also highlighted, as it uses only instantaneous phase current signals measured at the distribution substation. The methodology has been shown to be effective across various fault resistance values, fault types, fault inception angles, and fault locations.